There's this specific moment when you're using an AI agent.
Yeah.
Maybe you're trying to debug some code, or you're asking it to reorganize a massive folder. You type in your command, you hit enter, and then you just wait.
The blinking cursor.
Right, the blinking cursor.
Mhm.
And maybe a little spinner. And then eventually text starts streaming onto the screen, I've fixed the bug, or I've moved the files. And for most of us, that gap, between the request and the result is just a complete black box. It's magic.
We treat it like a magic trick. We put a request in the hat, pull a rabbit out. But if you're actually trying to build with these things, or even just use them effectively as a developer, believing in magic is a massive liability. You really need to know the mechanics.
Which brings us to our source material for today. We're doing a deep dive into a technical blog post that was published just yesterday, January 23rd, 2026, by Michael Boland from OpenAI. It's titled, Unrolling the Codex Agent Loop.
And this is such a good look under the hood of the Codex CLI, the command line interface. But really, it's a masterclass in the architecture of pretty much any AI agent. Bolen isn't talking about the model's personality.
No.
He's not reviewing how funny the bot is or something. He's talking about the harness.
The harness, I really like that term.
It's the perfect distinction, isn't it? We so often confuse the model, the brain, like GPT 5.2, with the agent. But the agent is the software. It's the machinery, the harness that surrounds that brain and gives it hands to actually do work on your computer.
So our mission today is to strip away that magic. We're going to dissect this agent loop. We're going to figure out how it builds memories, how it uses tools, and why these obscure engineering terms like statelessness and compaction determine whether your AI assistant is a genius or just a hallucinating mess.
And honestly, understanding this loop is the difference between being a passive user and like a real power user. When you know how the machine thinks, or rather how the machine processes, you know how to drive it.
Okay, let's start with the core concept then, the agent loop. Boland calls it the heartbeat of the system. In plain English, what is actually happening here?
At its simplest, the agent loop is a choreography. It's an orchestrator. Picture three distinct players. You've got the user, that's you. You have the model, the raw intelligence, the brain in a jar. And then you have the tools, the terminal, the file system, a web browser. The loop is just the logic that passes messages between these three parties.
Okay, but it's not just a straight line, is it? I say do X and it does X. That feels way too simple.
It is too simple. It's almost never a straight line. Think of it like a turn in a game, but a single turn can be incredibly complex. Let's walk through a real scenario to make this concrete. You type, list all the files in this folder and tell me which is the largest.
Simple enough. So that's step one, the input.
Right. The agent takes your text, but, and this is so key, it doesn't just email that text to the model. It wraps it in this huge amount of context, a whole briefing dossier, which we'll definitely get to in a minute. Then comes step two, inference.
Inference, that's the translation layer.
Exactly. The agent sends all that text to the model. The model translates it into tokens numbers, does its complex math, and predicts the next most likely tokens. Now, here's where the fork in the road happens. Step three.
The response.
The response. So the model has two choices. It can send back an assistant message, that's it talking to you, here's the largest file. Or, and this is the important part, it can send back a tool call.
A tool call. Okay, this is the crucial bit. The model realizes, I don't actually know what files are in your folder. I'm a brain in a jar. I can't see your hard drive.
Precisely. So it sends a structured request, something like, please run the command LAL. It's asking the agent, the harness, to do it.
So the agent sees this request. It sort of pauses the conversation with me. It runs the command in the background, gets the list of files.
Yeah.
And then what? It doesn't just show me the list, does it?
No, and this is the loop part. The agent takes that list of files, the output, and it adds it to the conversation history. It effectively says, okay, model, you asked me to run alls, and here's the result. And then it sends everything back to step two.
It goes back to the brain.
It goes back to the brain. Now the model has the file list. It analyzes it. Maybe it sees a subdirectory and decides, wait, I need to check inside that folder too. So what does it do? It issues another tool call.
So a single question from me could trigger, what, 5, 10, maybe 20 of these internal cycles?
Almost easily.
It reminds me of, sending an intern to the archives. I say, find me the contract from 2024. I stay at my desk. The intern goes to the basement. That's a tool. They open a box. They realize it's the wrong box. They open another one. They find the paper. They read it. And only then do they come back up the stairs to speak to me.
That is a perfect analogy. And that delay, that thinking time where the spinner is just spinning, that's the intern running up and down the stairs. The agent is investigating, testing, and refining before it ever commits to an answer for you.
And the agent loop is just the set of rules that lets the intern know they're even allowed to go to the basement in the first place.
Exactly. Without the loop, the model just hallucinates an answer because it can't actually check anything.
Okay, but for that intern to know where the basement is, or even who I am, they'd need some onboarding, a briefing. And this gets to the next section of Boland's post, which I found really, really revealing. Building the brain, or as he puts it, constructing the prompt.
Right. This is where the magic really falls apart and you see the pure engineering. It's less like talking to a person and honestly, more like programming a server.
Because I always assume that when I open a fresh chat and type hello, the model just sees hello.
Oh, if only. If it only saw hello, it would be useless. It wouldn't know it was a coding assistant. It wouldn't know it had access to your files. It wouldn't even know what year it was.
So before I even touch the keyboard, the agent is building this massive hidden prompt. Boland lists out the ingredients. He calls them JSON objects, and they all have different roles.
Right. Think of it like a chef preparing a very specific recipe every single time you talk. It's like a layer cake of authority. You have system, developer, user, and assistant.
Okay, let's bake this cake. What's the bottom layer? What's the very first thing the model gets?
The first ingredient is instructions. These usually come from your configuration files like a config.tomlail on your local machine, or the model's base prompt, maybe something like GPT-5.2-codex prompt.md.
So this is where it says you are a helpful coding assistant. Be concise, don't break things.
Exactly. It sets the personality, the ground rules. Then you have the tools. This is huge. The agent basically acts like a waiter reading the specials.
Yeah.
It explicitly lists every single capability it has. I have a tool called Shell. I have a tool called Web Search.
Wait, hold on a second. This includes things like MCP, right? The Model Context Protocol.
Yes, absolutely. MCP is a standard for connecting an AI to external data. So let's say you installed a custom weather tool via MCP. Every single time you start a loop, the agent has to send a definition of that tool to the model. I have a tool called GetWeather. It requires a latitude and longitude.
And if it doesn't send that definition, the model literally doesn't know the tool exists.
It has no idea. It's like the intern has a toolbox, but if you don't give them an inventory list, they won't know there's a hammer in there. They'll just try to pound the nail with their hand or tell you it's impossible.
That's wild. It's constantly reminding the model of its own hands. So what's next in the stack?
The environment context. This is really cool. The agent injects a message that just says, you are currently in this folder, user's name project steep dive, and you are running in a shell.
That explains why when I say make a new file, it knows where to put it. I used to think the model could literally see my computer, but it can't. It was just told in plain text, you are here.
It's all just text. It's all a story we were telling the model. And then there's one last critical ingredient, the sandbox.
The safety rails.
Right. A developer message that lays out the rules of engagement. It says things like, you are not allowed to access these networks, or you must ask for permission before running a delete command. This stuff is derived from files like workspacewrite.md.
I was just so surprised by the sheer volume of this invisible text. Boland points out that the client, the software in your laptop, builds almost all of this.
And that's a crucial distinction for privacy and for control. The server OpenAI or whoever might decide the order of the messages, but your laptop provides the content. It means the behavior of your agent is largely defined by the files on your local machine. If your config.toml is wrong, your agent is basically broken.
Okay, so we've built this briefing dossier, the agent wraps it up, ships it off. Now we get to the actual mechanics of talking.
Boland gets pretty technical here about how the CLI actually talks to the API. He mentions that Codex sends HTTP requests to endpoints. And, we usually think of this as the OpenAI API, but he makes a great point that this harness doesn't care whose brain is in the jar. The endpoint could be localhost.
Right, you could be running Llama 3 or something on your own machine with all Llama.
Exactly. The agent loop works exactly the same way. It just needs an endpoint that accepts a prompt and returns tokens.
Speaking of returning tokens, let's talk about that typing effect. We see the words appearing one by one. I always kind of thought that was just a UI choice, to make it feel futuristic.
It's not just for show, that's streaming. Technically, it's server-sent events, or SSE. The response comes back as a stream of data packets. And Boland distinguishes between two types of events here, which is really important for debugging.
Okay, what are they?
First, there's response.outputText.delta. That is the text you actually see appearing on the screen, the chatting,
Look, then there's the invisible stuff.
right? Response.function call. When that event comes down the stream, the UI usually doesn't show you anything. But the agent just wakes up, it sees that event and says, oh, I have a job to do. I need to run some code.
And this leads us right back to that recursive thing we touched on earlier. I want to really nail this down because I think it's the hardest part to visualize. Bolin explains that when a tool is used, the agent creates a whole new input array.
Yes. And this is where we start running into real engineering headaches. Let's just trace the data. Turn 1, you send the briefing, plus read the readheb. Turn 2, the model replies with a tool call. Run cat readme.md.
Okay, got it.
Now the agent runs that command. It gets the text of the readEB file. So to get the next response from the model, the agent has to bundle together 1, the briefing, 2, your original request, 3, the model's request to run cat, and 4, the actual text of the readm.
So it's cumulative.
It sends all of that back.
It's like a snowball rolling down a hill. Every time the agent does something, the snowball just gets bigger.
And if the conversation goes on for an hour, I asked A, you did B, here's result C, then I asked D, you did E. The snowball becomes an avalanche.
And this leads us straight into the engineering challenges Bolin focuses on. A quadratic problem.
Quadratic is a very scary word in computer science. It means the cost grows significantly faster than the time. If the history doubles, the computation doesn't just double, it quadruples. If you have to resend the entire history of everything we've ever said, plus every tool output, every single time I want to say, cool, thanks, we are going to burn through data, money, and time so fast.
Because the model has to reread the entire novel every time I add a single sentence at the end.
Exactly.
And eventually we hit a hard wall, right? The context window. The model's brain is only so big.
Correct. So Bolin outlines 2 major solutions that Codex uses to fight this. And the first one is a combination of statelessness and prompt caching.
Let's break those down. Statelessness first. That sounds kind of forgetful.
It is, by design. Codex does not use a previous response site. It doesn't say, hey, server, remember what we just talked about? Add this to it.
Why not? That seems like the obvious way to do it.
Well, it's efficient, sure, but it's a privacy nightmare. If the server remembers your context, that means your code, your secrets, your chat logs are sitting in RAM or a database on a server somewhere in a data center.
I see.
By being stateless, the client, your laptop, holds all the data. You send the full transcript for processing, they process it, they send back the answer, and then poof, they forget it. This is what enables a system of zero data retention, or ZDR.
That makes a ton of sense for enterprise. If I'm a bank using this, I do not want OpenAI storing my session state indefinitely.
Exactly. But as we just said, sending the whole book every time is slow and expensive, and that is where prompt caching saves the day.
Okay, how does that work?
Bolin explains that the model is smart enough, or really the infrastructure is smart enough, to recognize the prefix. It looks at this incoming avalanche of text and says, hey, wait a minute, I've seen the first 90% of this before.
Because the briefing dossier, the instructions, the tool definitions, the early chat history, none of that has changed.
Right. It's like rereading a book where only the last page is new. You don't actually reread the first 300 pages. You just verify they're the same, and you skip to the end. The model caches the heavy computation for that first part.
So it only has to do the heavy lifting for the new stuff.
Exactly. Bolin calls this a cache hit, and it turns a quadratic problem into a linear one. It makes the agent feel snappy and cheap. But, and here's the big warning for all the power users listening, you can break the cache.
How do I break the cache?
By changing the past. Or, more commonly, by changing the environment.
Give me an example.
Remember those tool definitions, the list of ingredients from the start.
Yeah.
Okay, so let's say you're 10 minutes into a debugging session. It's going great, cache is hitting every time. Then you decide to enable a new MCP server. You add a Google search tool mid-conversation.
Okay.
The agent has to insert that new tool definition at the beginning of the prompt list.
Oh, no. It changes page 1 of the book.
Exactly. It changes the briefing dossier. So the server looks at the incoming text and says, I don't know this sequence. This doesn't match my cache.
So it's a cache miss.
And it has to recompute everything from scratch. It's slower, it costs more, and it feels sluggish. Bolin even mentions a bug they had early on with MCP tools where the tools were just listing in a random order.
Random order?
Yeah. So one time weather was first, the next time shell was first. That tiny change meant the prefix was different every single time. It completely killed the cache. They had to fix the cum to ensure the list was always alphabetical just to save the cache.
That is such a subtle engineering detail. It really shows how fragile these systems can be under the hood.
It really does. If you're building tools for these agents, you have to be obsessive about consistency.
Okay, so caching saves us from the speed issue. But eventually, no matter how fast it is, we're going to run out of space. The context window is full, the bucket handles 128K tokens, and we're at 129K. What happens then?
Compaction.
This sounds like a trash compactor.
It's actually a very accurate name. When the conversation gets too long, Codex uses a specific endpoint, responses compact.
What does that do? Does it just, like, delete the old stuff?
Not exactly. It takes the long history, all those back and forths, the tool outputs, the chatter, and it summarizes them.
Mm-hmm.
But here's the fascinating part. It's not just writing a text summary like, we talked about Python functions.
It's not. No.
Bolin mentions it creates a new list of items to replace the old ones. And inside that list is a special item with type compaction. And inside that is a field called encrypted content.
Encrypted content. That sounds very sci-fi.
It is. It preserves what he calls the latent understanding of the conversation. Think of it like a ZIP file of the model's brain state. It's an opaque blob of data vectors, numbers, that the model can read to remember the nuance of the conversation without needing the thousands of tokens of literal text.
So it's creating a synthetic memory.
Yes. It frees up space in the context window so you can keep working, but you don't lose the thread of the discussion.
That is just wild. Like, okay, imagine if you and I talked for hours, and then we took a break. Instead of handing you a transcript of what we said, I just downloaded a vibe into your brain that contained the feeling and the conclusions of everything we discussed.
That's a really good way to put it. It allows the agent to maintain continuity essentially indefinitely, as long as it can keep compacting the past. But it begs the question, what is lost in that compaction?
Right. Can I unzip that file? Can I read the encrypted content?
You can't. It's totally opaque to the user. It's strictly for the model.
So we've unrolled the loop. We've seen the prompt construction, all those ingredients. We've seen the streaming conversation, the cache hits, and finally the compaction. It's not magic. It's a very complex assembly line.
It's a cycle. Construct a massive context prompt, send it out, get a command, execute the work, add the result to the stack, and then repeat.
So why does this matter to the person listening right now? The person who just wants to use the tool to write some code.
I think understanding this helps you debug your own interactions. If your agent is acting weird or it's not following instructions, you can ask yourself, did I confuse the harness?
Right.
If it's slow, maybe you're causing cache misses by constantly changing your toolset. If it's forgetting instructions, maybe they weren't in your config.tl in the first place, so they never made it into the briefing dossier. Or maybe you've hit a context limit and the compaction process just missed a specific detail you really needed.
It turns you, the user, from a passive consumer into an active participant in the loop. You start to understand how to feed the machine properly.
Exactly. You stop yelling at the intern for being stupid, and you start checking if you gave him the right map to the archives.
I want to leave everyone with a thought based on that compaction idea. Bolin wrote that the encrypted content preserves a latent understanding.
A powerful phrase.
It really is. We are moving from human-readable text, our history, to a machine-readable thought that we as humans can't read. If the agent is summarizing our work into a format only, it understands. What nuances are we losing?
That is the big question, isn't it? When we hand off our memory to the machine, we have to trust its translation.
Or, and maybe this is even more interesting, what are we gaining? Is it seeing patterns in our work that we didn't even put in the text? Is the encrypted thought actually smarter than the transcript?
That's something I hadn't considered. The summary might actually be better than the raw data.
Something to mull over next time you see that little cursor blinking, waiting for you.
Definitely.
Huge thanks to Michael Bolin for the blog post, Unrolling the Codex Agent Loop. Go check it out if you want to see the JSON schemas for yourself. And hey, go check your config.tomls file. You might be surprised what instructions you're sending out into the void.
Always good to check under the hood.
Thanks for listening to The Deep Dive. Catch you in the next loop.